Hi guys, I wanted to go ahead and talk you through a few of the problems from this week's synthesis lab. This is normally what we would do in class, is go over a little bit of strategy, a little bit of how to set problems up, and actually do a few problems. So before we get into a specific problem, oh, I'm just adding more of the same page. Sorry. I did want to talk just a little bit about how to approach synthesis problems. This is something you should have covered in Organic 1. I know we do it in Organic 1. I'm just going to use a blank page here. Zoom in. Here we go. Okay. So there's not one specific and only way to approach these problems. You can certainly look at it from, we are going from A to B, and along the way, right, we might hit, intermediate 1, 2, and then product. And if you can see that path from the beginning, that's great. And the way we approach some of the problems today, we will do that as well. But a lot of times it is helpful to look at it in a retrosynthetic way. So to start with B and work backwards. Now, if you do retrosynthetic analysis, something that you'll notice, and Klein uses this approach, is the retrosynthetic arrow. This thick arrow is indicating that we're going backwards. I do not want you to provide me with an end product of retrosynthetic analysis. You can absolutely work through it backwards this way, but then I want you to go back and provide me with the A to B, right? Go back and show me forward, the forward progression. There are also a couple of different ways that you can show this. Let's say that we're doing this very generic. A goes to intermediate 1, intermediate 2, and then to B your products. You can show me like this, where you do 1 reagents, 2 reagents. However, it is much easier for me to grade and find partial credit if you show me the individual steps. If you show me 1, here is the intermediate product 1. 2, whatever those reagents are, here's intermediate product 2. Let's say we have the third step, that brings us to our product B. This is much easier for me to find the partial credit if I know those intermediates that you are trying to make. You don't have to show them to me. You can do this, but this is just a little bit of insight into how I grade. There is always potential for partial credit in a synthetic analysis. And if you show me the steps and the intermediates, that's helpful. Now, absolutely don't show me mechanisms. I do not need to see curved arrow notation here. But reagents and intermediates are a great thing to show me. Another thing that I want to mention here, if you had Organic 1 with me, you might remember this. I am happy to look at your work and give you feedback if you send it to me before the day it's due. This can even be just the night before it's due. If you send it to me the day it's due, I don't promise to give you feedback. Every one of you should be able to make 100% on this, because if you do it ahead of time, I am happy to check it for you. I want this kind of assignment to help you get prepped for exams. And so if you wait till the last minute to do this, I won't look over it. But if you finish this a few days early, I'm happy to provide you notes and feedback. So please take me up on that offer. Okay, so I want to start with 1A. Something you're going to notice in 1A, there's no aromatic compound here. we're just going from an alkane to a diene. So you're going to have to utilize organic 1 reactions. Organic builds on itself. You can't only focus on new material. You are constantly building off of what you learned in the past. So as you are working through your synthesis problems, I highly recommend getting out some of that review material that I sent you, or that I posted for you for Unit 1. Look at your alkene reactions, your alkyne reactions, your organic 1 review sheets. You're gonna need it when we do synthesis. So when we look at this very first problem, you can do retrosynthetic analysis, but this is one where I actually think it's not a bad idea to start at the beginning. Why is that? It's because you're starting with an alkane, and that right there is a gift, because you only know through organic 1 reaction that starts with an alkane. And that is to add a bromine to it, right? We don't have a whole chapter on alkane reactions. You learned the one, radical halogenation. And so let's think about what happens if we treat our alkane. Let's get rid of that right there. If we treat our alkane with either NBS or Br2 and light, where is that bromine going to go? Now, it's going to go on a more substituted position, and it frankly doesn't matter which one you pick. We pick one of the secondary positions and go with it. You're going to get a mixture, but ultimately it's not going to matter because of what we're going to have to do in the next step. So I'm going to go ahead and just say, all right, the bromine is going to add to that center carbon. Why not? And then, actually, you know what? No, I'm going to use my noggin here. There are 2 carbon 2 positions, so I'm probably going to make more of this one. Again, it doesn't matter. The next step is going to make that unimportant. How do I go from an alkyl halide to an alkene? This was probably the first chapter you really got into organic reactions. This is an elimination. So if I want to eliminate, and I can choose which way I want that bromine to eliminate, there are several different ways to complete this synthesis. You can choose to go Zaitsev or Hoffman here. Whichever one you choose, you will be able to continue and complete this one. That's the cool thing about synthesis. There are often more than one correct answer. Now, sometimes you will work yourself into a corner and you have to you have to backtrack. But this problem has several correct answers. So let's just say I want to make the Hoffman product. Well, how can I make the Hoffman product? I need a bulky base. So you're going to learn that potassium tert butoxide, or just the tert butoxide ion, this is one of my favorite bases because it does not act as a nucleophile, so it will only eliminate, and it will give you the Hoffman product. Now, you could have used sodium hydroxide and in water, so like a protic solvent, and you could get the Zaitsev product. But this is what I've chosen because this is oddly my favorite base. Okay, so now I have a double bond in place. It's this one right here, guys. Okay, so what do I do next? Well, I'm going to repeat the process, but I can't use Br2. If I use bromine with a double bond, it is going to add across the double bond. So now I have to use NBS and light. Remember, NBS, N-bromo-6-cinnamide, does the same thing as Br2. It keeps the level of Br2 low so you don't have that competing reaction. Now, it is selectively going to go to this position because not only is it secondary, it's allylic. And the bromine wants to go to the position where the radical intermediate is the most stable. So secondary is more stable than primary, but the resonance involved with the allylic position is even better. So now once we've got this set up, we've got our bromine in place. Now it's one more elimination. Now, in this case, it does not actually matter which base you choose because it is not going to eliminate towards the double bond, because accumulated double bond, as you recall from earlier in the unit, is less stable. So you can use potassium tert-butoxide again, or you could use sodium hydroxide, right? Or methoxide or ethoxide. You just need a strong base here. If you want to really avoid SN2, you also can just, put a protic solvent in with it. If it is potassium tert-butoxide, it's not going to substitute, so you don't have to worry about that. Now, everybody should get the points for 1A because I've given you one method here. You could go about it on your own, though, to practice, and you may find that you get a slightly different answer. And that's important for you to recognize, and I've said it already here, and I'm going to say it again. There are often more than one correct answer. When I give you solutions to synthesis problems, that is possible solutions. So if you think you've come up with something, and let's say your classmate came up with something different, don't automatically assume that one of you is wrong. Ask me. You might be able to tell there. You definitely might have made a mistake, and we need to figure that out and talk about it. But you may have just found separate correct paths. Now, I'm going to let you do 1B on your own. Notice again, you're starting with an alkane. So you at least know what the first step is. In this case, you are making a carbonyl as well as the alkene. So you know how to put that alkene in place now. I want you to think about how you can make a carbonyl from an alcohol, right? So go through your organic 1 reactions. You could get to this position here, and instead of eliminate, you could do a substitution and an oxidation. So I'm going to let you guys work on that one on your own. Now in C, I want you to really read the directions. To make this, you are starting with A and B. I want you to recognize that you could redraw A like this, and you could redraw B like this. Think about a Diels-Alder and what kind of product you would get, and then what would you have to do to that product to make the final product asked for in C. A, B, and C are supposed to all go together. All right. Now, when we get to 2, I think it's A through F. Yeah. We are starting with benzene, or we're starting with a modified benzene, and we are adding to it. So you are going to be using your reactions that you learn in chapter 17 and 18 to complete this. You may have to add in some reactions from organic 1 still, but a lot of this is going to be focused on our new material. So let's do 1 together. Okay. Let's go ahead and, they're all just so much fun. Okay. All right. We are going to go ahead and do 2A. Now, we've got benzene, and we are making styrene, right? So we want to add this 2-carbon piece. And so we need an alkylation. The issue here is when you do an alkylation, right? And just let's think about this generically. If you are going to add in R Cl with a little bit of aluminum trichloride and put in that R group. This RCl, this carbon needs to be an sp3 hybridized carbon. You cannot just put in that double bond. So we can put in a 2-carbon piece, but we have to think about adding in the double bond afterwards, right? So I'm going to get you started on this one, and I'll let you finish it, and then we'll do one other one together. Okay, so let's say we want to put in our 2-carbon piece. We can't put in a double bond. This is not an acceptable starting material. That it's got to be an sp3 carbon that the chlorine is on. So we're going to start with an ethyl chloride and our Lewis acid. And that is going to substitute, right, electrophilic aromatic substitution. We're going to sub out one of those hydrogens for our ethyl group. Now from here, I want you to think about the 2 steps needed to put in that double bond. Based on what we did in the first problem, hopefully that's standing out to you. So you guys will finish 2A. Just getting you more practice with those org-1 reactions. I'm going to let you guys work on 2B on your own. And let's do 2C. 2C? Let's do 2C together. Okay. We have to add 2 things to our ring. So we have to think about how to add an alkyl group. So we're doing an alkylation. And we're adding an amine. So hopefully you have finished your chapter 18 videos by now, at least up through, I think, the second to last part. You know that you can't add an amine directly, but you can reduce a nitro group, right? So we do know how to add a nitro group. When you add 2 groups, you have to also think about the directors, right? This is a meta substitution here. So I have to think about what's going to go on first so that I can get that meta direction. I also have to think about what's allowed. So there's a few different issues going on here. If I think about the amine, this is an ortho para-director. If I think about the ethyl group, this is an ortho para-director. Okay, so neither one of them are meta-directors, so this must be a little bit more interesting. What about if it was a nitro group? Well, a nitro group is a meta-director, but there's a problem. Nitro groups won't allow Friedel-Crafts reactions if the nitro group is present, right? That's a big limitation of Friedel-Crafts. So even though a nitro group is a meta-director, I can't put it on first because then I can't add the carbon. Okay. Oh, so it's like, what am I going to do? Well, I have one other option that I learned when I learned about Friedel-Crafts that will help me here. And that is the Friedel-Crafts acylation. So instead of an alkyl group, I have an acyl group. I still need my aluminum trichloride. And that's going to add a 2-carbon piece, but with a carbonyl. And what's cool about that carbonyl is that's a meta-director. So now I can add in my nitro group. So I'm going to do my nitration conditions, HNO3, H2SO4. It is going to add to the meta position. And now I can reduce both of these groups with the Clemmensen reduction, right? A Clemmensen reduction is HCl and a zinc mercury amalgam. Yeah. And then it might have chloride in it. It might just say zinc chloride. I can't remember off the top of my head right here, but I think it's some sort of zinc mercury amalgam. Look up Clemmensen reduction. The Clemmensen reduction will reduce your carbonyl to your alkane piece. And as it turns out, it'll also reduce your nitro group to your amine. And so what's important here is that we add the carbon group, we add the nitro group, we add them in an order that gives us a meta product and that we reduce at the end. So I hope that walking through a few of these problems helped. You're at least going to rack up some points here. Work on these problems. If you hit a stumbling block or you just have no idea how you're doing, or you come up with one you feel really good about, shoot it over to me. I'll look at it and I'll give you some notes. All right. I look forward to seeing you guys again next week. Have a good week and good weekend.